Do you ever worry about how climate change may affect the systems we all rely on every day and everywhere? In this video, I'll show you how we embed climate considerations into the systems we design and use. And then we assume they will remain reliable and safe regardless of their age and history. I go back to first principles, and I consider how assumptions about climate may be baked into these systems. And I consider how climate and age can eat away at their reliability and safety. I don't do this to scare you, but I believe that when we understand these factors, we're all better able to cope. Most designs start with a basic understanding of the loads on the system. These loads could include many factors, such as weights that the system must bear, pressures, and the like. For many systems, the designer also includes consideration of the climate loading, based on historical data. For the rest of this video, I'm going to focus on climate loads because this is where we get our most questions. Here we see the base loading of the system as a simple bar graph. As a starting point, designers will make sure the system will have enough capacity to handle the expected loads. We see this in the capacity bar. At first, it is the same height as the expected load, but there is uncertainty associated with both the design load and the theoretical capacity. So the designer will add safety margins. This ensures that the system has built-in buffers to deal with the uncertainty. It's not uncommon to see systems with 10% or more safety margin. These margins may be explicitly stated, or as often as not, they're included in the design without detailed documentation. They may be even buried in the coding of design models. We can see the safety margin in the capacity bar growing in height. This results in a buffer between the top of the load bar and the top of the capacity bar. In the real world, the capacity will erode over time, first from general wear and tear, as we can see by the capacity bar decreasing in height, and then weathering can also eat away at capacity, reducing the height of the bar even further. This increases the uncertainty about the amount of safety margin remaining. If the design has sufficient built-in headroom, the system should remain relatively robust. Load can change over time as well. Systems are typically designed with a set of uses in mind. For example, a bridge's capacity will account for the typical vehicle weights expected over its useful life. However, things can change. Populations grow, new industries are established, and the loading on the system may be different. We call this change of use. The loading on the system may be greater than its original design load. We can visualize change of use as an increase in the height of the load bar. Once again, there may be uncertainty associated with this change of use. But even so, because of the built-in safety margins, the system should still be safe. Over time, the actual safety margin between real-world loads and capacity is uncertain. Generally, we know the system is safe because it supports normal use and maintains an acceptable level of service. But the climate is changing. We now experience weather events larger than we have ever seen before, so climate loading can exceed current operational norms. And we see this in the growth of the load bar. This results in an unstable condition. When loads exceed capacity, the system will eventually succumb and fail. The extent of the failure will depend on the magnitude of the weather event and the overall preparedness of the system's owner. If the owner evaluates the system with an eye to climate change, they can take steps to mitigate the risk of failure. This is where climate risk assessment shines. It helps owners identify system weaknesses and then take steps to address them. In this way, they're better able to cope with climate-related impacts on their systems. The assessment shines a light on the uncertainties and provides clarity about the magnitude of the risk. Everyone's better prepared.